Hello and welcome to the second topic for week 9. We're going to today to look at ideal gases. So we looked at temperature and what that meant at a molecular level in the first topic. This one will continue that on, but looking at gases now. This lecture is slightly less content. You will have noticed the first topic had a little bit more. There was a slightly more than one normal lecture's worth of content. This one in turn is slightly less. I will probably do a single video for this lecture and then a second one for the question. So rather than 3 parts, there'll be 2 parts for this video. Jump over to our slideshow. Ideal gases. Goals for this lecture are to understand the assumptions of the ideal gas model. Remember, that's a common thing in physics, that we take a model where we make certain assumptions just to make our analysis a bit easier, but we do have to keep that in mind, because if we don't meet any of those assumptions when we start to look at a real scenario, we have to say, hold on, what's that going to do to our model? How's it going to affect it? We want to be able to use the gas laws to predict the properties of gases. And we want to look at the amount of substance in a sample versus the number of atoms or molecules. So we've already been doing that when we looked at the atomic mass unit and counted how many atoms or molecules there were in a substance based on their atomic masses in those. We're going to continue that discussion and bring in some new concepts here as well. States of matter. We're familiar with all of these. This should just be revision for everyone, hopefully. Solid, its shape and its volume is defined. It's just, it is a solid thing. And then fluid covers the other 2, liquids and gases. Liquids will stay the same volume, but will take the shape of their container, whereas gases will change shape and volume to fill whatever container they're placed in. The state of a substance is determined principally by its temperature and pressure. That's just a statement of fact. We should all be familiar with that by now, and that should be no surprise. Actually, we haven't talked too much about phase conversions yet, phase changes. So the temperature and pressure bit, the pressure bit might be a bit unexpected for some of you potentially, but hopefully that's not too surprising there. We will talk more about phase changes when we look at heat. So I told you all to remember the concept, the idea of a gas being made of all these little particles flying around through space. The gas atoms, the gas particles are atoms or molecules that are in a gaseous state. And if you think of gas in that sense, then pressure is pretty straightforward. Pressure is simply the force of all the collisions from all those little gas particles inside the container hitting the walls of the container. They hit the wall of the container and bounce back off, and that's a force because there's some area inside the container. All these particles hitting it in a certain amount of time will provide a force so that you get an average force per or over time, and that is the force over area that's giving us that pressure. So that's all the pressure is. Pressure needs a force applied over an area. In this case, the force is from the collisions, and the area is just the whole inside of the container that is facing the gas. So that's all pressure from a gas is. And if we keep that mental picture, that idea of these particles flying around and just bouncing into the walls, because they just fly in a straight line until they hit something. They might hit another gas particle and go off in a different direction, but eventually they'll hit a wall and bounce off that. There's nothing else, there's no other forces on these particles. There's gravity, but we'll ignore that for now. There's no other forces inside the container except for those collisions, right? Since gases are compressible, some of the equations we used for fluids don't really work anymore. We talked about pressure as a function of depth. It's rho GH for a fluid when it's incompressible, which is usually a liquid. But when it is compressible, we can't do that anymore. We can't say, well, the pressure here is just going to be the depth of gas. We can't use that relationship. So we have to think about some other ways we can investigate these phenomena. We've got pressure, volume, and temperature as 3 things about our system. If you've got a bunch of gas, then those are the 3 things that will define it. You've got the volume of the container you're putting it in, you've got how much pressure it's exerting on that container, and you've got the temperature of the gas in the container. The other thing that we haven't, that I haven't included here, but we will come to, is the number of gas molecules. How many molecules are there actually in that sample of gas that you've got inside the container? But to start with, let's ignore that. We're just going to assume that however many there are stays the same. That's our assumption for now. But the amount of gas you've got doesn't change. We're going to talk about the relationship of these three properties, specifically each pair at a time. And the process of investigating these and coming up with the results and the relationships that we're going to see was empirical. That means it wasn't derived from some law. It was just given as a result of investigation. So they are empirical. Remember, that's what empirical means. So empirical gas laws is often the name given to all three of these laws that we're going to do. So we're going to look at each of these pairs in turn. We're going to look at pressure versus volume, pressure versus temperature, and volume versus temperature. So what we're going to do is we're going to say from these three things, let's hold one constant and see how the other two relate to each other. And we'll do that for all of them. So first of all, let's fix our temperature. Now, that's an easy one for us to do because we can do it without needing any heating apparatus. And so that's pretty simple. We just get some kind of container that is airtight or gas tight, whatever gas we're using, that we can change the volume for. And let's think about what happens to the pressure in this case. I've done little diagrams here that hopefully help visualize it. Again, keeping in mind this idea of gas as being a whole bunch of particles flying around inside the container. So on the left-hand side, we've got a bunch of gas particles in a container. I've only drawn, 6 particles. Obviously, there's going to be more than that. It's just as an example to remind you to think of it that way. What happens to the pressure if we push down on the lid? As I said, we're keeping the temperature constant. Remember, temperature is the kinetic energy of the particles. So in this sense, keeping temperature constant means the particles still travel with the same speed. So we've got the particles still with the same speed, but now they're in a smaller container. We've still got the same number of them because we haven't taken any gas in or put any in or taken any out. So what's going to happen to the pressure if we change that volume? Hopefully, you'll all have realized that we'll get more collisions. If we've still got the same number of particles traveling with the same velocity inside that container, they're now going to hit the wall more frequently because the walls are all closer. When you're on the bigger container on the left, when you're in it rather, your particles have to travel further to hit one wall and then bounce off and then hit another one than they do on the right-hand side. Now, they're still all traveling with the same speed, but they're going to hit the walls more frequently. Remember that the pressure comes from all those collisions. If the particles are providing more collisions, then that means that we've got more pressure. Now, you may stop and realize that there is going to be less area as well, but the area is, because you've pushed it down, you've lost some of these walls here. The gas particles can no longer hit part of the wall, but overall the area decreases by a small amount, whereas the number of collisions increases by a big amount. So the number of collisions still goes up more than the loss in area, which means you get a higher pressure. Boyle's law. That's the name given to what we've just discussed. Right, so we've got temperature being held constant, then pressure is inversely proportional to volume. So if you want to write that as an equation, it's P is proportional to 1 over V. Hopefully you've all seen that proportional sign there. P is proportional to 1 over V, and then PV is constant is another way to write that. So that's Boyle's law. We don't expect you to memorize the 3 names. By all means, go ahead. The names, though, while still important, they do refer to scientists who were involved in discovering these laws. More important is the concept, understanding why this happens. So if you can understand why Boyle's law is true, even if you forget that it's called Boyle's law, you're in a pretty good position. All right, so now let's fix the volume instead. The volume cannot change now. Instead, what we can do is change the temperature. What's going to happen to the pressure? All right, so the volume is fixed, but now the temperatures are increasing. Remember what temperature means in terms of gas particles. what's going to happen to the pressure? Well, we're going to get stronger collisions, and they'll happen more often since the particles are traveling faster. If you've got a particle that has more speed than an identical one, the one with more speed will have a bigger impulse in order to change the momentum, to bounce off a wall. Right, so it'll have a bigger impulse, so that means you're getting a bigger force applied by this particle, but also because it's traveling faster, the distance that it has to cover to get to the next wall after it bounces off one is less. So we've now got more forceful collisions and they're happening more often. So therefore we're going to get a higher pressure. So what we see is that if we hold the volume constant and increase the temperature, then we get an increase in pressure. And this one is called Gay-Lussac's law. Again, remember the name if you can. It's worthwhile to remember them if you are going to continue studying physics, especially thermal physics. As I said, if you can understand the concept and be able to reason and explain this, that's more important than remembering the name. So again, in words, if volume is held constant, then pressure is directly proportional to temperature, or as an equation form, we've got P is proportional to T, or you can write it in a straight line form, P is equal to MT plus C. So pressure is proportional to temperature, P equals MT plus C. I'm going to assume you're all comfortable with straight lines. That's basic mathematics that we expect you to be fairly confident in terms of writing equations. So if something is proportional, it means you've got a straight line relationship. Constant pressure now. What we've got here is a volume adjustable canister. So the gas is inside this canister, but the seal of it, the lid, can move up and down. Right? And we've got atmospheric pressure on the outside. Atmospheric pressure on the outside. What we're going to do is we're going to heat it up. So these particles are going to get hotter. But remember that this can move. So whatever happens, this gas will have to stay at atmospheric pressure, because if it was higher, then the force upwards would be greater than the force downwards from the atmosphere, and the seal would move up and make the volume bigger. If it was lower pressure in here, then the atmosphere would push downwards more than the gas is pushing upwards, and the lid would go down. So what's going to happen is the question. What will happen to that lid? What's going to happen if we increase the temperature while keeping the pressure at atmospheric pressure? And the same argument applies for any pressure. We've used atmospheric here as in our example because atmospheric is the easiest one to deal with. We can just do it in a lab. But obviously you could set up a specific pressure enclosure and do this at any pressure. Hopefully you've all realized that the increased temperature will, just like we talked about with the previous one, will result in more forceful collisions. But what that's going to do then, as soon as it tries to increase the pressure, we said that the lid is going to move. So if the pressure goes up a tiny bit, instead the lid will go up a tiny bit. All right, so that we're at atmospheric pressure again. If we're still heating it up, then the lid will go up a bit more. Heat it up, go up a bit more. As long as we keep applying heat, we keep giving those gas particles more energy, then they will keep pushing that lid further and further up until the point is reached where the pressure from outside, from the gas particles at standard air pressure and temperature outside, are colliding with the same amount of pressure, same net force across that area as we're getting from the gas particles inside the canister, right? We need that equilibrium to be reached, the net force on the lid to be zero, and that means the pressure on either side to be the same. If these particles are hotter than the ones in the atmosphere, then that means that these ones will hit less frequently in order to provide the same pressure, the same net force, and that means that we need this gas to expand so they've got further to travel, because if we made it smaller, they'd hit it more frequently and we'd get a higher pressure. So hopefully, again, you can understand that reasoning, and that one is called Charles's law. If pressure is held constant, then volume is directly proportional to temperature. And again, we can write that as an equation, either V proportional to T, or in straight line form, V equals MT plus C. So this last one, volume is, a few of them. Few of them can be used to think about absolute zero. We mentioned absolute zero when we talked about Lord Kelvin. He said, let's come up with a scale that says when these gas particles or any particles have absolutely no kinetic energy, we have 0 Kelvin. That was his idea for his temperature scale. And if they've got no kinetic energy, that means there would be no collision. If there's no collision, then there's no pressure. So we can use this idea of no pressure or no volume to figure out where absolute zero actually would be. That's how we know that it is at negative 273 degrees Celsius. So just a moment on that constant pressure, either no pressure or no volume. If you've got a constant volume, so the volume can't change of our little canister, then as the particles slow down to no energy at all, they would just simply fall to the bottom of the canister where they would sit with no energy and not colliding on anything, right? So there's nothing at all hitting the inside of the container. So we've got no pressure. On the other hand, if we had the one where the lid of the canister can move up and down, it's a movable seal, then as the particles slow down to having no energy, the atmospheric pressure would just push the seal all the way down to the bottom and would get absolutely no volume. So it depends on which thing you're holding constant as to whether you'd go to no pressure or no volume. But either way, we can use these laws to come up with an experiment where we determine absolute zero. And indeed, that's something that we do in the physics labs. Again, with this being an online course for this semester, we will have to come up with some workaround for this, but I am hoping that we can do one of the virtual labs, whether it's just a video of me doing the experiment or potentially a virtual lab for this one. But you can set up experiments like this. They're not too hard at all. So in this example here, we've plotted pressure and temperature. So we've kept volume constant and we've measured the pressure. And we've just taken a bunch. In this case, I've drawn 5 on there, but it would be however many you take, the more readings you get, the more reliable your result. And then you fit that straight line and the intercept, in this case, the intercept on the x-axis, because we get to 0 pressure. At 0 pressure, that means we're at absolute zero. You can see that in this case, it's about negative 273. That's what it should be, and so I've drawn this to match, but in the real world, you'd take your data and you'd see where that comes out. Hopefully it would be around about there. But again, you could do that the other way. You could do it with the volume if you had the volume adjustable setup and change the temperature that way. So a quick little exercise. Suppose we have a sample of gas. If we increase the temperature, what happens to the pressure? So take a moment to think about this exercise. Pause the video if you need to, but take a moment to think about it, and then we'll discuss on the next slide. The 4 options are: it increases, it stays the same, it decreases, or not enough information to decide. So what happens to the pressure if we increase the temperature? I'm going to move to the next slide now. So hopefully you've all made your discussion with yourself and or partner if you've got someone else studying with you. The correct answer is we don't have enough information. Remember that in all of those discussions we just did, we always held one thing constant and then changed the other 2 to see what would happen with them. If we haven't said that we've held one constant, then we don't actually know. We don't know what has gone on with the volume. In this case, we were talking about pressure and temperature. If we increase the temperature, what happens to the pressure? Well, if the volume stayed the same, then the pressure would increase. If the volume got smaller, it would increase even more. But if the volume got big enough, quick enough, if the volume got bigger more quickly than the temperature went up, whatever that ratio needs to be, then you could end up that the pressure goes down. So you could have that you're actually giving it more energy, you're heating it up, but you're increasing the volume so quickly that you actually get a lower pressure resulting. So without any more information being given to us, we cannot tell what would happen. Right, as I just said, as the point of that exercise was, we have been treating one of them as being constant, PV or T as constant. What happens if none of them are? What happens if we don't have constant pressure or volume or temperature? What if all 3 can or are changing? Well, we still need some way to figure out what's going to happen in these scenarios. We can't just say, oh, physics doesn't handle it, let's ignore it, go do a different problem. No, we need to be able to figure that out. So we have to try and come up with an equation that ties these together. Right? As I was just saying with the previous example, if you're increasing the temperature and you increase volume enough, then the pressure will decrease even though temperature is going up. Likewise, if the volume isn't increasing enough, the pressure will increase, which is what we expected if we held the volume constant. So the ideal gas equation is the way to tie all of these together. PV equals NKT. Now we've introduced two new terms here. We've got pressure, volume, and temperature still in our equation, but we've now got N, which is the number of gas particles, and K, which is Boltzmann's constant. Now the number of gas particles is important because the more particles you've got, the more collisions you're going to get, and the more collisions you get, the higher the pressure. So that has to be part of our equation. Because if you kept everything else the same and just took half the gas particles away, you're going to have half the collisions suddenly. If you've got half the collisions, you've got half the pressure. So you're going to get this direct relationship between the number of particles and the pressure. We often ignore that one in terms of changes because we don't often change the number of gas particles in a sample. It's a lot harder to do than it is to just heat it up or cool it down or change the volume. That said, we're now going to start thinking about the number of gas particles, and we will start to introduce some problems where we do change the number or compare two systems where the number is different, is slightly easier. And the other thing, the Boltzmann's constant, that's just the number that it has to be to make the equation work. If we go and measure the pressure, the volume, determine how much gas there is through whatever method, through mass or some other analysis, and measure the temperature, and we make all four of those things be the correct numbers, we can figure out what K has to be in order to make this equation true. And it turns out it's just always one constant, right? It's just always Boltzmann's constant. We should check this against those three laws. We already saw those three empirical laws, and we know that they're all true. We saw them work, well, we thought about them, but you could go and see them work. And so we have to make sure that this ideal gas equation, if we're claiming it works for everything, it still has to hold up those three Charles law, Gay-Lussac's law, and Boyle's law. It still has to work for them. So let's just think about them. If we hold the pressure constant, let's hold pressure constant, then we've got volume is equal to NKT. Right? So volume is proportional to temperature. If temperature goes up, volume goes up. And that's exactly what we saw. Let's now hold volume constant. We have P is equal to NKT. Well, V, I guess we could divide by V. So we get P is equal to NK over V times T. NK over V is a constant if we're holding a volume constant. And we get pressure is proportional to temperature. Temperature goes up, pressure goes up. That's what we expected. And lastly, if we hold the temperature constant, then this whole thing on the right-hand side is a constant. And that means that if pressure goes up, volume has to go down, or if volume goes up, pressure has to go down. And again, that's what we expected. So we've got all three of those laws do work with the ideal gas equation. So far, so good. The next step we're going to do is actually think about this N, the number of gas particles. What does that actually mean? Not what does it mean, but what can we do with that? Counting the number of gas particles isn't really possible, obviously. And even if it was, we'd end up with numbers that are really huge because there's so many gas particles in even a small amount of gas. And the solution is to introduce a new term called moles. Not the animal, even though those are cool. It is a number. A mole is just a number. So if you have 1 mole of something, then you have 6.02 times 10 to the 23 of it. So this can be a little confusing. A lot of people try and think of moles as a scientific term, as some specific constant. And in a sense it is, right? It is a constant, it's a number, but it's just a number in the same way that a dozen is a number. So a dozen means you have 12 of something. A mole means you have 6.02 times 10 to the 23 of it. So if you had a very large amount of eggs and you could count all the way up to 6.02 times 10 to the 23 eggs, then you would have 1 mole of eggs. You can have a mole of anything if you have enough of it. Just like you can have a dozen of anything if you have 12 of it. So that's all mole is. As I said, it doesn't have a unit, it's just a number. But we do often write mole, M-O-L, after it just to remind ourselves that we're talking about moles. Not actual numbers. So if I say I've got a mole of carbon atoms, I'll often write 1 mole, M-O-L, of carbon atoms, just to remind myself that I don't just have one carbon atom. Just like if you had eggs, you wouldn't say just one egg, you'd say 1 does eggs, right? So 1 dozen eggs, to remind yourself that it's 12 eggs, not just one. So it's just a unit to simplify counting the number of particles in your gas sample. This photograph here is quite an interesting one. It shows you how many you need of each thing in the balloon. It's full of helium. There is 1 mole of helium in the balloon. There is 1 mole of sulfur on that first dish, 1 mole of copper on the second dish, and 1 mole of mercury in that little glass jar. So it's just showing you that 6.02 times 10 to the 23, that's a huge number. 6 and then 23 zeros, or 0 and 2 and then 21 more zeros. So it's a huge number. And obviously atoms are tiny. Atoms are these ridiculously small little things. But when you've got that many of these ridiculously small little things, it becomes an amount that we can actually see and deal with. And that's the usefulness of the number mole. We now have a number of things that are so tiny that it becomes an actual usable size. It's a scale that's actually useful for us. Here's a question. If you have 1 mole of carbon atoms and 1 mole of O2 atoms, how many CO2 molecules will result if you combine them? So this question is really just an attempt to make you think about what we mean by a mole, as well as thinking about the idea of a molecule versus an atom versus a gas particle, even though it doesn't say particle in there. Obviously, if you've got a mole of carbon atoms, then you're adding it to O2 molecules, you're making a gas, which will be gas particles. So what happens to this? You've got 1 mole of carbon atoms, 1 mole of O2 molecules. How many CO2 molecules will result if you combine them? So as usual, I'm talking a little bit padding for time, just so that you can hopefully have a think about this question, come up with an answer yourself. But I will obviously discuss this in a moment, and that moment is now. The solution is that you will have 1 mole. So you've got a mole of carbon atoms. You've got 6.02 times 10 to the 23 carbon atoms. And to every one of those, you attach an O2 molecule. Well, you don't attach it, you chemically combine them and they turn from carbon and O2 into CO2. But that means that every 1 carbon atom is now part of 1 carbon dioxide molecule. So if you had 6.02 times 10 to the 23 carbon atoms, you've now got 6.02 times 10 to the 23 carbon dioxide molecules. And the same reasoning applies to the oxygen molecules, the O2 molecules. Each one of those molecules is now part of 1 carbon dioxide molecule, so you've still got the same number. So you had 1 mole of of carbon atoms, 1 mole of O2 molecules. You combine them, you now have 1 mole of CO2 molecules. So hopefully you can all convince yourselves of that, but it's just a little thought exercise to hopefully get used to dealing with moles, to think about what's going on with those. This has nothing to do with anything of importance, but it's just a fun little bit of trivia. And some people find that it helps them remember the value, although again, with most, as with all constants, you will be given these constants when you need them. But on the 23rd of October, from 6:02 AM to 6:02 PM, we celebrate Mole Day. I say we celebrate, I don't personally celebrate it in any real sense. It's just a fun thing to remember on the day. And of course, that is because 6:02 is the value, 6.02, and 10 to the 23 is our scientific notation. So October being the 10th month and 23rd day, 1023. We were looking at the ideal gas equation, and we said pressure times volume is equal to number of gas molecules times this constant, Boltzmann's constant, times temperature. And we said that will always be true. And now we've introduced this idea of moles, number of moles of a gas rather than the actual number of particles of a gas. And so we can change our ideal gas equation to be in terms of the number of moles. And all we have to do if we want to do that is change our constant K to be constant R. So instead of big N for the number of particles, we go to little n for the number of moles. And therefore, instead of K for a constant, we now have R for a constant. R is known as the universal gas constant. its value is given there, but again, you'll be given that generally. An extra little exercise for you, if you want to, is to figure out the relationship between K and R based on that relationship between the number of particles and the number of moles. Not something you have to do, but it's a good little exercise. You may occasionally see it in assignments or tests or exams, so do have a think about that one. So when you rearrange this, you put all the constants for the thing that are staying the same on one side and everything that's changing on the other. So if you've got PV over T, if you're going to change all three of them, then you'd put all of them on the left, and you'd leave NR or big NK on the right. And that means that if we've got two situations, then we know that PV over T initially is going to be the same as PV over T afterwards. This is just one way to solve it. You don't have to do it this method, but I do find that this is reliable, that most people are perfectly happy doing this. So it's a similar in a sense to the Bernoulli's equation. When we apply that, we say, for Bernoulli's equation, we say, here's our pressure term, our kinetic energy term, and our potential energy term. Figure out what they all total up to. That's a constant. And if we choose any other point in our system, we know they still have to add up to the same constant. And that's the same idea here. You put the things that can change on one side, figure out what that gives you for a constant for the system at that point in time. And then at some other point in time, after you've changed all the things that are going to change, you know that you still have to get that same constant out. So don't worry, we'll do some examples on that because that might not be perfectly clear yet. So one thing we haven't talked about is what we mean by ideal gases. We said that we have this ideal gas model. We've made some assumptions about our gas that allow us to state these laws, for these laws to be true. What are those assumptions? First of all, we're assuming gas particles have no internal degrees of freedom. So that is, we treat them like hard spheres, so little billiard balls. Internal degrees of freedom is a fancy way of saying some other way the particle could use the energy besides heat, besides temperature. If you give it heat, you give it some thermal energy. We're saying it has to be thermal energy. It has to be temperature. It has to be kinetic energy of the gas particle flying through space. That's not always realistic, but it allows our ideal gas equations to work. And the other thing is that when they collide elastically. So if you've got two gas particles and they bounce in midair, that's an elastic collision. They both go away exactly the same as they were before, but now the velocities and kinetic energies might have changed around depending on how they collided. And the same with the particle hitting a box wall. When it hits the wall, it comes away with an equal and opposite momentum in the perpendicular direction from the wall. So we're assuming all of that stuff is elastic. So there's no chemical reactions or long-range forces or any other stuff involved. We're just taking these nice, simple assumptions. And they're actually surprisingly good assumptions, provided we keep the density of the gas low-ish, right? Don't get too dense. Remember, density is the amount of mass per unit volume. So density of a gas is basically saying how many particles are you shoving into that container. If you don't shove too many in, the density doesn't get too high, and then we can actually say that the ideal gas equations hold pretty well. The other thing that we have to assume is that the temperature doesn't get too low. So this works well for most temperatures you would encounter in normal life or even basic science experiments. But if you start to get too low, then it starts to break down and we have to start considering some of the other aspects of the gases. So that's all the content for this lecture. We talked about pressure from a gas being about collisions. We talked about the three empirical gas laws, and then we tied them all together into the ideal gas equation. And then we introduced the term of moles as an alternative for talking about the actual total number of particles. So that's all of the content into one video. I will do another video on the questions, so there will be a second part to this, but not a third part. So that's the end of this one. The questions are in the slideshow in the sheets. the PDF that you can find on stream. So do go and have a go at them now, or as usual, I will sort of pad my videos out a bit. You can watch the video and do the problems as we go along that.